Observing a falling object. The purpose of this lab was to observe a paper ball falling. Then, using Newton's second law, create a computer model to predict the future motion of the object, specifying the initial conditions from observation and assuming the significant forces to be the weight force and drag force alone. The resulting graph matched the experimental data at the very beginning and the end position, but for the most part, it vastly mispredicted the motion. This lab will use Newton's second law, the final velocity equals the initial velocity plus the net force over the mass of the object times the change of time, and the position update equation, the final position equals the initial position plus the average velocity times the change in time, for the same purposes as last time, updating the position and producing a position versus time graph. However, velocity isn't constant, so the net force isn't the zero vector. Therefore, the net force will be found using the sum of the weight force and the sum of the drag force. The weight force is the gravitational attraction between the falling object and Earth, and is given by the negative mass of the object times 9.8 meters per second squared times j hat in the y direction, that is. Turbulent drag force is the force that acts against the object as it's falling and is given by a negative b, which is a constant found experimentally, times the velocity squared, magnitude of the velocity squared, times j hat. It acts in the opposite direction, and since it's correlated to velocity, it increases exponentially with time, playing a greater role later. The motion observed in this experiment was a paper ball dropping to the ground. It moved along the negative y-axis, and its position versus time data is graphed and charted here. For the first model looking at only weight force, we first look at the constants. The mass of the paper was found to be 0.0043 kilograms. And as seen previously, it starts at position times 0, and the velocity vector is also 0 since it was dropped, not thrown. Additionally, the gravitational constant is 9.8 and is moving in the y direction, given by j hat. The while loop takes the coded version of the aforementioned principles, weight force, Newton's second law, and the position update equation, and it runs until the point that the ball hit the ground, which is 0.583 seconds. When we run the model, this is what we get. When compared against the experimental data, it is unexpectedly under-predicting the position. This means that the gravitational force is not the only y direction force, or that it was miscalculated somehow. The first would have happened if the paper was thrown instead of dropped, and the second might be explained by underestimating the mass, though this number is very small. Nonetheless, I'll add a negative drag to match the final position and see what happens then. So to add drag, a new constant b is added. It's found via trial and error and produces the final position when added to fnet. I went ahead and wrote it in vector form. As mentioned before, it should go in the opposite direction of gravity, but something went wrong. So this is the updated while loop with the drag force going in the same direction as gravity. And if we want to run it, it looks like this. And as you can see, once it finishes running, it'll give you the updated position, which is negative 1.73, which matches the tracker file, which is negative 1.764. In comparing the two model predictions, yellow here is the one which includes drag and the experimental data. The end now matches up, but there's still that discrepancy in the middle, which is the exact same. This is probably attributed to an additional y force, which I didn't take into account. Suppose for a moment that the data was normal, our model should underpredict originally and say that the position goes further. That way, as you can see, a negative drag force brought the line down. A positive drag force would bring it up to better match the data if it was under. Throwing the ball is like starting at a non-zero velocity. So, if the ball was thrown, it would look like the graph was shifted to the left. These data points would actually move over here. A good comparison is actually my model data to my experimental data. This would be a thrown ball, this would be one that's dropped. Additionally, the drag would make a greater contribution earlier since it's dependent on velocity. This means that terminal velocity would be reached sooner. Velocity versus time is the derivative of the position versus time graph. Terminal velocity is when drag force equals the gravitational force, canceling each other out, and the velocity becomes constant. So, in order to find this, we look for a linear portion on the otherwise parabolic curve. Near the end of this one, it's still parabolic. However, for this one, it does look to flatten out a bit, but that's not enough for me to determine that it's terminal velocity. I'm going to go ahead and say that none of my models predict terminal velocity because there is still a curve in them. So, using Newton's second law and the position update equation, as well as calculations for net force, I could not predict the future motion of the object, but I got a pretty clear picture of what went wrong and how it might be fixed next time.